Hello, good morning, and see you again. Today we will have our lecture number 8 for this course, which is on the topic of microfabrication integration and assembly. So we have looked into the process of MEMS fabrication. We have covered the photolithography, we have covered the etching, and today we will look into the what will be the process of assembly and integration and the existing process of semiconductor, some terminology on the integration and assembly of chips and semiconductor devices. And then we will proceed with this lecture today on this topic of integration and assembly. So in MEMS devices, we know that there are a few things that we need to combine. One is on the mechanical property, mechanical aspect, and we have to look into electrical aspect, optical for some cases, and thermal function in some other cases as well. So the main thing might be mechanical and electrical, but this might be according to the device that we are designing. And this requires reliable integration with electronics and packaging. So if you see here, so normally MEMS device will sit somewhere inside or in the packaging. So we need to package it accordingly because MEMS device is in principle is quite fragile in comparison with macro size devices. So because of that, we need to have a proper packaging in terms of main device. And at the same time, we have to address the electrical circuitry in terms of contact point, for example, circuit line, and the thermal effect and thermal function of the device, etc. So therefore, the assembly is very critical for performance, reliability, and cost. So we are not just talking about the performance only, but also when we consider the device in terms of commercial aspect, we need to consider the cost of the assembly and how we can design the process, the assembly process and the integration process, so that is cost effective and will be something, on top of the performance required. So here, in this figure, we can see that we have a few components in the packaging. So in this package, we have MEMS device at the center. So we have a platform for the MEMS. Then here with this package, you can see the shock absorber. So as well, to accommodate any impact to the device itself. So the package substrate to cover, and it might be hermet package that which is airtight, etc. So that is a part of the design that you have to consider when you try to have integration and the packaging of the MEMS devices. So we see that MEMS device is very small. So this is a monolithic speaker. It's MEMS speaker. It's quite common nowadays. We use it in many devices, our handphone, smartphone, for example. We have some other things like this is the construction. So you have electrode, you have membrane, another electrode and chamber. So it's construct into this kind of speaker. Then you need to package it accordingly so it becomes quite robust in terms of handling shock and handling impact and whatever maybe environment they are in operation. So MEMS integration levels. Basically, there are a few MEMS integration level. One, what is we call as system on chip or SoC, where we have MEMS devices with a CMOS on the same substrate. So from the beginning, the design is about designing the MEMS and CMOS at the same time, meaning to say from from the design stage, you have integrate the CMOS and also the MEMS devices at once. And the process will be going through on the same substrate until the end. And next is a system in package, SIP. So MEMS plus IC, integrated circuit, and packaged together as well. And it's, the next is hybrid integration, multiple chips interconnected. Sometimes due the complexity of the operation, later on we might need a few chips to be integrated with the MEMS devices. So, for example, the process of MEMS we have looked before. You need a wafer to process the MEMS. Then we design the MEMS devices or chips or whatever is it on the one silicon wafer. So in the case of a system on chip, we might design from the beginning that these MEMS devices also come with a CMOS or IC or with integrated. So then you have LSI wafer, large scale integrated circuit wafer, then kind of a bonding with a wafer bonding here. So then you transfer the MEMS and LSI wafer after removal, etc. So that is some of the process that happen with MEMS devices. Okay, system on chip in detail. So system on chip is an integrated circuit that combines nearly all the electronic components of a computer or other electronic system onto a single microchip. So this is we consider as single microchip. This compact design integrates a central processing unit or CPU, memory, input-output, ports, and other features onto a piece of silicon, leading to a smaller, faster, and more power-efficient devices. So we know that if we compact everything together, so we have a small device instead of we require wire bonding or any other connecting wiring or connecting footing, etc., to the device, or with some connecting using soldering, etc. So that might be might makes the device become bigger. But here with this kind of SoC, we can have a smaller, faster, and more power-efficient devices. So in this case, we have a MEMS and sensor actuator here. Then we have RF antenna for communication. Then we have a CPU RAM and test wrapper and analog RF. So this will make this small device and operating device by itself. So system on chip is a single SoC can contain many different parts, including one is a processor cores, typically one or more processors, which can include microprocessor, microcontrollers, digital signal processor, or specialized accelerators. So in our previous case here, we can see that a few components. And memory, for example, various types of memory, such as read-only memory, and graphic processing unit also can be integrated, a dedicated unit to handle graphic rendering and accelerate tasks related to image processing. So you can see that nowadays with a small camera, for example, the MEMS CCD, you can also get the image processing done straight away. And interface, a communication protocol and ports to allow the SoC to communicate with external device network. So we have include, for example, USB, Wi-Fi, Bluetooth, and so on. And digital and analog modules, a component like digital to analog converters and analog to digital converters that also can be included in the device itself. And power management unit, circuit designed to regulate and manage the power consumption of the entire chip, which is critical for battery-powered device. So these are all the possible component parts that can be integrated on the scale of SoC. And by integrating so many features in one chip, basically, we can have a major benefit over traditional multi-chips design instead of every single component separately. So with this kind of design, one is a space optimization that make the device become smaller by placing all components on a single die, reduce the physical size and footprint of the device itself. And power efficiency, consolidating components reduce the energy required for data transfer between separate chips. And higher performance, the short distance for on-chip communication result in less latency and higher processing speed. Imagine you just have a connector of a few nano or a few microns between the chip rather than a few millimeter using wired connector. And lower cost, while the initial design cost can be high, mass production of a single highly integrated chip is more cost effective than manufacturing and assembling multiple separate components. We know that in MEMS, we use a wafer, and in wafer processing is a batch processing. Then if you integrate everything from the beginning, everything is fabricated at the same time, then it reduces a lot of cost in terms of to assembly in the later stage. Improve reliability, fewer physical connection, and a more integrated design lead to a more reliable and of overall system. So the next type is a system in package, SIP. A system in package, SIP, is a single component that integrates multiple dissimilar integrated circuit and passive component within a single package to perform the function of entire electronic system. So SIP offer a miniaturized, cost-effective, and space-saving solution, especially for complex space-constrained applications like smartphones, by combining various functional elements on a common substrate. For example, here we have a few chips, a few components. So we just package it in one package, a small package of a component, including a lot of things. In comparison with SoC, we have everything on this one chip, basically, but this is in terms of package. So, and hybrid integration. So what is hybrid integration? Hybrid integration is the more advanced technique of combining multiple chips, often made from different materials or manufacturing processes, into a single high-performance package. This approach, also known as heterogeneous integration, overcomes the physical and economic limitation of building an entire system on a single chip or monolithic. Monolithic meaning if you use just a single, wafer, for example, that is monolithic, but heterogeneous is with different types of materials and different types of chip, basically, or components you try to integrate. So this is IC and this is MEMS. Then you try to integrate together with MEM and IC. So, and in this case of using a MEMS integration, there are a few types of integration. You can be lateral, by you connected the circuit or component in lateral manner. But of course, if you want to save more space, you can go up, meaning to say you are stacking the device. So we have now a 3D chip, for example, by stacking the MEMS or the electronics components in vertical way. So in MEMS, in order to improve the performance, in order to have a more compact devices, in order to have a more power, good power consumption. So this might be an approach of which is nowadays that makes things high performance of computing and high performance of devices. So you see that the integration in vertical manner save a lot of space. Instead of you go side by side, then you just stack on top of it. So, but this process require a lot of careful attention in terms of packaging, in terms of connecting the electrical circuitry, and in terms of reliability, in the bonding of wafer silicon, for example, then it is quite difficult. And to have a, let's say in this case, later on we will look into TSV, through silicon via. So that also quite a difficult process. Here you can see we have a true silicon via, which is meant to connect electrically between these two stacking devices or a component. So in other cases, there are also wire bonding. So wire bonding can be, I mean, sometimes we have to have both because of the complexity. But if we can have a true silicon via, then it might reduce a lot of hassle and of connecting the electrical component together, and also to reduce the power consumption and efficiency of the device. So you can see here MEMS integration level. So for example, we have two wafers, LSI and the MEMS wafer. I mean, this is the every single components. So we can have a wafer bonding with LSI. So this will create one whole chip of MEMS device and the LSI. So this integration also need to be done in a very careful manner, because the adhesive bonding is not that straightforward. It requires a lot of attention. And then the alignment of the wafer, the component at the bottom, and this MEMS device also require a lot of, I mean, careful of alignment. So because we are dealing with a micrometer and nanometer scale alignment. And for example, you can have a piezoelectric MEMS switch on top of this, and you have your LSI wafer at the bottom. So now you have one single package hetero integration chip, where after the bonding, you do maybe some processing, then with the wafer level sealing is attached tightly, then you dice into one single package of chip with the function MEMS devices, so such as a microphone or speakers, MEMS speakers, or MEMS microphone. So wafer level bonding normally will be done using anodic or fusion or eutectic, or using adhesive bonding. And die attach and wire bonding can be done, as I mentioned before. You do wire bonding to integrate the electrical circuitry. Then we have flip chip and true silicon via. We're going to look, and wafer thinning and dicing and stacking. So this is kind of typical process of MEMS. You have silicon substrate. We have learned this before. And deposit materials layer. You do the patterning to get the device done. Then you remove certain material using etching. Then sectioning or dicing. You dice every single component, for example. Then you have your single component. Then whether you attach with a package, and you have your packaging. So the packaging is what we have shown as in the MEMS microphone. So wafer level bonding, it needs to be done in a very careful manner. As I mentioned before, we do it in a clean room, for example, in order to avoid contamination. And we have to do wafer cleaning preparation, the surface alignment. As I mentioned before, two things, which is the alignment and also the cleaning of the surface. So then with external activation, for example, you use heat and RF, etc., and you use force, or you use vibration, or you use EV in order to bond. If you have a certain maybe certain adhesive or certain brazing, etc. And direct wafer bonding, you use anodic using Si glass. And what happened is fusion. So hydrophobic and or hydrophilic vacuum or plasma assisted high temperature or low temperature chemical assisted bonding of glass. So basically the bonding of Si glass. And mediated wafer bonding is anodic bonding using deposited film. For example, you deposit something of metal or any thin film in order to act as adhesive to bond these two wafers. So it can be solder, it can be, what type of solder you can use, and also gold silicon eutectic, and bonding using glass film or polymer assisted bonding. So that is some of the method to bond wafers. And for die attach and wire bonding, we know that in some you have die bonding here. You have die here. You have your chip. Then you try to bond it with the chip to the die. So, but the connector might be the wire that you're using. But in some other cases, you can use flip chip bonding. Flip chip, as the name appears, it is about flipping the chip on top to the back, meaning to say you arrange your foot with a connector. So this flip chip will connect directly instead of using wire to connect the electrical circuit. So this kind of save a lot of space rather than you have to have a space in this manner. Then you are only now at this small footprint for the device itself. So that is the difference between flip chip. So again, we have talked about through silicon via. So through silicon via is a hole on the silicon substrate that pass through the top and bottom of the substrate so that you can connect whatever design on the top of the device on or the substrate, and to be connected if you are stacking the chip, so or stacking the device. So the stacking will help with a lot of device to be integrated together, and the use of silicon via will reduce the footprint of the device as well as improve the performance. So here you can see that the CMOS chip through silicon via then connected to the bottom part of this. And let's say you have a flex PCB as well, CMOS chip, then optics chip, everything connected through silicon via. So in this case, you can avoid of using wire bonding. So maybe wire bonding will be required when the whole chip to be connected to the other package. So here is the difference between wire bonding, as I mentioned before, and also the flip chip design. So here you have to bond with using wire bonding to the outside of this or to this pad using wire. Instead of that, you have a flip chip to be connected directly using solder bump, for example. So, and the process of MEMS, wafer thinning, dicing, and stacking is a kind of a common process we should do in order to get the certain level of size and dimension. And thinning, for example, we might start with the silicon of 400 micron thickness. Then according to the design, we might reduce to 300 because of the etching, etc. on the structure, everything we need to do accordingly. And dicing also because it is about producing in the a batch production. In one wafer, you can have multiple or many small devices in batch. Then you want to dice it into single a single package or single component. Then this is a example of silicon wafer which you have pattern of your device, for example, and then you need to slice it, to dice it into single package, a single component to be packaged, maybe. And the packaging requirement. So as earlier, as mentioned before, the packaging need to be done in order to avoid environmental effect to the device, and also to make sure that it operate at the optimum condition. So hermetic sealing is one of it for protection from environment. And also in the requirement for the packaging is to have a stress control to avoid warpage and drift for the component, and electrical interconnects with low resistance, and thermal management for stability. So what is hermetic sealing? So hermetic sealing creates an airtight, basically, moisture-proof enclosure that protects sensitive electronic components from environmental factors like gases, liquids, and other contaminants. This is crucial for application where reliability is non-negotiable, such as aerospace, medical implants, and defense systems. So this is an example of hermetic sealing where you have a seal here. It can be polymer, it can be metal, etc. in order to avoid airtight sealing when you have a seal ring maybe round shape here. Then you have your MEMS device connected to the package and connect to the outside using electrical connection. And as I mentioned before, you can use solder, you can use brazing. So here, in this case, brazing is used, and a seal ring and the ceramic with the ceramic components. And this is some design. Kyocera multi-layer ceramic provide the hermetic structure. So the package, the packaging, it can be ceramic packaging. So it's quite common for ceramic packaging because at a certain extent, we want a certain device need to be isolated from electrical connection to prevent short circuit. Then you use ceramic packaging. And ceramic packaging basically is quite stable because of it can withstand high temperature, and also is a robust materials. And commonly, in hermetic sealing, glass to metal seal is used, formed by bonding glass to a metal. Match seal use material with a similar coefficient of thermal expansion, while compression seal rely on the metal compressing around the glass during cooling, creating a robust seal for high pressure application. So match seal we use to have a controlled thermal expansion, meaning to say the use of the both material with quite similar thermal coefficient expansion. And ceramic to metal seal creates a strong, robust seal ideal for high stress, high temperatures, and high pressure environment. Then we have laser welded seal. A laser beam melts the interface between a component and is covered inside an inert gas chamber. So the process highly localized and create a precise airtight joint upon solidification. So it's like you are melting in a welding, but you are using laser to melt the material. Epoxy seal, certain epoxy resin can form hermetic bonds with various materials, including metals and plastic. So they are effective for application with a more limited operating temperature range. So if the operating temperature is not so high, so the use of polymer resin might be suitable, because we know that the temperature of resin is not that high in comparison with ceramic and metals. So we need to consider the stress control as well. So effective stress control during MEMS packaging is critical to avoid warpage and drift, and which are caused primarily by mismatch of the coefficient of thermal expansion and materials viscoelasticity. So MEMS devices with their delicate moving components are highly sensitive to this package-induced stress that can deform the chip and degrade performance. So if we have a material which is with high coefficient of thermal expansion, so if it's operate in the high temperature range, for example, from 10 to maybe 80, so the expansion of the material might cause a bending and thermal stress. This thermal stress can damage the component. So that's why the stress control design, if we cannot avoid of using certain materials or required to use certain material which might be different in terms of coefficient of thermal expansion, then we might need to consider a way in order to release the stress if this condition happen. I mean, the fluctuation or the operation in high temperature happen. So, for example, here we have some MEMS device with a cap, and this is with a low stress design. So you are not connected with a package that is, I mean, can withstand. This is your package, basically, and this package might not affect that much in terms of the deformation of the casing or the packaging on the top. Okay, so it's avoid the stress to the component itself, the MEMS device. So in this case of ultra low stress, so you can see that this is connected directly, but in this case, this is quite kind of not connected in a way that it is, let's say, this component deform. So you have still some design to avoid to be affected on this base package. So that is one way of designing from the beginning in order to have a package which is at low stress, and so on and so forth in terms of the how you design the package to avoid or to control the stress. And the thing with stress control is, as I mentioned before, is about coefficient of thermal expansion. The most fundamental approach is to select packaging materials such as the substrate and the adhesive with CTE values that closely match the silicon MEMS die, and a lower CTE mismatch reduce thermal stress as the device cools from the bonding or curing temperature. So it's not just about when the device at the operating condition, but it's also about when you try to fabricate the materials or the device itself, you might get the device into stress if the process is not controlled in manually controlled. And low stress adhesive using soft low modulus adhesive like specific silicon instead of a stiff epoxies for die attachment can reduce the transmission of stress from the package to the MEMS die. Some die attached film offer lower stress development than traditional epoxy. And the next is control of adhesive properties. So the viscoelastic properties of polymer-based adhesive can cause long-term drift in MEMS devices, even at room temperature, due to the continuous stress relaxation and offset. This effect can be characterized and minimized through careful material selection and also a process control as well. So, and next is on the low resistance electrical interconnects. So, of course, we want to have the interconnects to be efficient and low resistant. So we need to design and to choose the materials accordingly so that it will be a low resistant interconnect. So in MEMS, achieving low resistance electrical interconnects is critical for high performance and reliability. So we know that if it gets heated due to resistance, then it might cause some damage. Common strategies include using advanced wafer level techniques such as copper fill through silicon via. So we have learned about silicon via of creating hole through a silicon surface from top to down or from upper to the bottom, so that to connect another chips. And materials innovation such as low temperature bonding with a gold tin alloys, and the ultimate goal is to minimize resistance and parasitic effect while withstanding demanding operational and environmental conditions. So you can see here some example of low resistance interconnects design, where you can have, let's say, thin film here, and on your substrate itself, then you connect with a 2D racetrack windings, for example. Then this is a solenoid design. Okay, so this is the, some general example of materials. And through silicon via, I have keep telling about through silicon via. So through silicon via, a foundation technology for achieving high density, low resistant vertical interconnects in 3D integrated MEMS and electronic. So through silicon via here, this is the example with a copper. For example, you have your MEMS wafer on top, then you have your CMOS IC at the bottom, then you have a solder bump to connect to another maybe PCB or another chip. So what happened here is, if this is not connected through this kind of through silicon via, you might use wire bonding, for example. You might use some other means to connect using electrically, but with through silicon via, you can just stack this together, and the footprint is small and the interconnects is short, so that you can improve the performance. And wafer level bonding. The wafer level bonding techniques are used to package entire wafers simultaneously, allowing for the direct integration of electrical interconnects during bonding process. I think I have explained this before. And optimize contact materials and design, minimizing contact resistance in MEMS switch and relays is a crucial performance. Researchers have explored novel design and material to achieve extremely low value for this. And again, on the through silicon via, the process involves creating vertical channels as shown here. So this it might look normal here, but for us to fabricate this kind of through silicon via is a very challenging, because the process of making it into nano or micro scale is quite difficult, and to make it straight in terms of the processing also very difficult. So it's a kind of challenging task and also an achievement. So insulating the channels with a dielectric layer like silicon dioxide and filling them with highly conductive metals, most often copper. And through silicon via, TSV dramatically shorten the signal path. If you see here, from here directly to the bottom, or to this component as well, rather than if you want to use wire bonding, you might use wire bonding through outside, and the wire will be longer. And this improves signal speed and reduce power consumption. TSV are particularly available for integrating MEMS devices with a control electronics and same chip, or in the stack configuration. So the stack configuration has made possible a lot of high performance devices. And for wire bonding, wafer level bonding, this technique uses a thin film of a metal alloy, as I mentioned before, such as gold tin, between two wafers. When heated, the alloy melts and form a strong bond that also function as electrical interconnects as well. So using the gold tin alloys allow for low temperature bonding, which prevent thermal stress from damaging temperature sensitive MEMS devices. So MEMS devices normally is quite sensitive, so we don't really expose it to harsh environment or high temperature. And techniques like copper to gold or copper to copper thermos compression bonding creates reliable, low resistance connection. And for example, a zero level chip cap package was demonstrated using copper tin gold metallic joints with a low temperature thermal compression bonding to provide vertical interconnects as well. So this low temperature pressure-free techniques use electroless deposition to create uniform microbumps. It is particularly promising for application with high density interconnects through ensuring the consistency of the bumps array remain a challenge for a very small pitch. So we know that we have a solder bump, but the thing is to make the solder bump also a challenge, and also to connect at the nanoscale or micro scale also another challenge. And pitch refer to the distance between two solder bumps, for example, and to maintain that in manually also quite challenging. Challenges in achieving low resistance interconnects and high processing temperature. Many traditional bonding techniques require high temperatures that can damage temperature sensitive material or introduce thermal stress, leading to reliability issues. So certain component might deform, might get damaged due to high temperature. And for example, some materials has a low Curie temperature. So such as a piezoelectric, if it's exposed to high temperature, you might lose the piezoelectric property. So material stress, the coefficient of thermal expansion mismatch between different packaging material and the MEMS device can induce stress. So this stress can affect the device performance, particularly in sensors. And defect and yield, immature manufacturing process for technologies like TSV. TSV is nowadays is quite matured basically, but it's still a difficult task to get is done, can lead to defect, including a void or a poor insulation, which increase resistance and lower overall device yield. And scaling and density, as MEM and integrated circuit become smaller and denser, interconnects must shrink to match. This increase the difficulty of manufacturing as smaller gaps and features can be more prone to issue like bridging. Bridging meaning later on you have a short in terms of electrical circuitry, or later on when in operation some bridging happen due to electromigration of the materials. So another thing is on the thermal management for stability. So as I mentioned before as well, and to have a package with a stress free or low stress to the component is very crucial. So that is where we need to have a proper thermal management. You can use heat sinks. You can use a way of material that can kind of transfer the heat faster if it's occur. Then a way of try to isolate the temperature or the heat from the device itself. So that is a few ways by material selection, by design, etc. We can also try to do the thermal management in order to maintain stability of the device. The thermal management is critical for stabilizing microelectronic MEMS and counteracting the negative effect of temperature variation, such as thermal stress, material changes, and signal drift. So a range of active and passive techniques are used to achieve thermal stability depending on specific application. So active meaning we have some means of like force cooling, etc., in order to have the device in a control temperature. And you can see that we have a lot of materials as a thermal interface normally used in electronics packaging, for example, phase change material and thermal pads. So this can be used accordingly in order to address the temperature or thermal management in the device itself. So for example, thermal grease and thermal adhesive and thermal gel and thermal solders. Basically, this can be used in order to channel the heat from certain device or certain area in order to avoid damage to the system. And another thing is on the challenges of miniaturization and manufacturability. So it's always a challenge because we try to produce from time to time to make it smaller. Things become smaller and smaller, but of course we want to have the same or improved performance as well. So at the same time, it's not just about making the thing smaller, but the manufacturing side, the machinery, the process needs to be able to cater for the needs of this miniaturization as well. Then we will look into this compatibility with standard CMOS. These are the challenge, and packaging induced stress and reliability issues and cost trade-off between wafer level and chip level assembly. So this is typical workflow of MEMS process. Basically, from laser cut, for example, you have your materials designed and developed with certain pattern. Then you try to assembly or integrate with certain components. Then you do lamination, and then you get your device done. But of course, people try to design it in a way that try to accelerate and try to speed up the process. And this is maybe you call it back-to-back adhesive instead of the cut. These two, you from the beginning, you try to attach together, for example. So this might reduce certain steps and make it simpler rather than you attach one by one in this manner to stack the devices. So we look into certain applications of MEMS integration. So for example, we have our smartphone, etc. We have accelerometers in the smartphone, microphone, MEMS microphone. We have MEMS speakers, etc. in our smartphone nowadays. So packaging. So packaging is an issue. Let's say this is a microphone. At a certain extent, you need to have the microphone to have opening so that it can function as a microphone. But at a certain extent, you want to package it to protect the components from dust, from humidity, etc. So that is the challenge where you need to have opening to the inside. But I mean, for this device to function, but at a certain extent, you need to have packaging to protect the device itself. So this is a pressure sensor, for example, different process. And of course, the application of MEMS, you have a pressure sensor for automotive. Then you have biomedical lab on chip, for example, and IoT device, low power MEMS sensors. So these are example of MEM that we are, commonly used nowadays, but we are not aware of it because it's somewhere out of our sight. So in automobile application, so a lot of MEMS devices can be found. You can find a pressure sensor on the tire, in the tire itself. So RF MEMS, etc., and LiDAR sensor, airbag accelerometers, GPS, so on and so forth. That maybe more than 20 sensors by MEMS in our automobiles. And in our smartphone, for example, this is quite old, 2010. It's already have a lot of MEMS devices. Let's say this is a MEMS speaker, as I shown before. So MEMS micro mirror, CMOS, etc., gyroscope integrated in the very small space in our smartphone. So TSV is considered one of the advances in MEMS packaging and MEMS design. So you can see here, you can stack a lot of chips and also device. If you can connect, let's say this is just 200 to 300 micrometer, so you just stack it up rather than you have to connect at the side or connect with some other means of connection rather than just stacking with a few micron thickness between the solder ball here. So this is a very kind of advanced achievement in the making the chips and the MEMS devices small and high performance. Heterogeneous integration, MEMS plus photonics plus RF in one package, and wafer level chips scale packaging. So there is also advanced trend nowadays and integration with flexible and wearable electronics. I think we commonly hear this flexible electronics nowadays as well. So this is heterogeneous integration. So it's just the opposite of homogeneous with the same material or the same package or the same component, but heterogeneous is including a lot of components, a lot of different materials, for example, to be connected in one package. So that is heterogeneous integration in MEMS. It include photonics, include radio frequency, for example, in one package. And this approach often more than Moore's. We are aware that in the Moore law, we try to have exponential growth or the double of the growth every year in terms of performance. But here we try to look into the things that will be beyond what can be achieved by Moore's law. And next is a wafer level chip scale packaging. So it's an advanced semiconductor manufacturing technique in which an integrated circuit is packaged, tested, and finalized while still on the wafer before it is cut into individual chips. So this is wafer, you produce a lot of, you design and fabricate here a lot of chips. Then normally, if you don't cut, normally you might cut this into single chip, then you integrate with your packaging. But now with this, you put on the package and try to dice it after you have packaged with this kind of chip as well. So this is the chip itself with a bonding to another component. So WLCSP provide a small footprints, creates a package that is minimally larger than the die, which is ideal for compact, high-density electronics like smartphones or IoT devices. And high electrical performance because it's eliminate bonding, wire bonding, and because you have a true silicon via as well, and minimize signal path length. This reduce inductance and capacitance, and cost-effective manufacturing because it's a batch production, batch fabrication process for the chip itself. And another, I would like to also introduce a case study of this kind of integration of MEMS devices. So in this case, we have this kind of silicon microstage, and to be integrated with piezoelectric actuator or PZT. So this integration, this is a kind of process that might be a little bit detailed in normal cases, but it's not at the chip level, but this is at the MEMS device level. So the silicon substrate, the silicon, this is with the size of 20 times 20 millimeter. So it's very small, and this is with the size of 8 millimeter. So it's very small as well. So the integration is difficult. So we want to integrate this PZT at this side and this side, okay, the location. So the positioning, we have to know how to make it slot at the right place, because this might have some tolerance in the between. So you have to prepare something that when you slot in a very small, it will be placed at the center as intended. So that is where some alignment can be made here. In this case, an alignment, this is a pattern create using photoresist. So a patterning using photoresist can create this kind of slot in. Then you can just place the actuator here quite easily. So this is at the back side of this. You need to also integrate in this to form in this manner. So this will be capacitive sensor in order to detect the motion. So at the back side of this silicon stage, there is another capacitive design circuit in like this thing. So in order to align with the top and the bottom. So this is glass, made of glass, this is silicon, and this is ceramic. So we need to integrate this kind of things together to put the PZT actuator here and to become in this assembly complete manner. So the process begin with the silicon stage produced, then with a coating of photoresist, then the sheet metal for the photoresist in order to provide interconnects, basically. This is the interconnects because this actuator need voltage, need to apply current, and also, potential needs to be applied to this actuator in order to function. So this is the circuit on this XY stage, and you have your actuator. It should be connected electrically. Then you have a bonding pad to connect to the outside. So this is the process. This is just to have the structure. Then you have your photoresist done attached to the stage, then with a sheet metal to the side, because see here, this is at the top and this is at the top, but here you need to connect at the side of this in order to it to function properly. So the side of this need to have a kind of conducting material or metals, and the side of this, of course, different side. This side also have to have a conducting material. So that is why you have a gold deposited on this side. This is covered, and you deposit gold on both sides of this. So on top is the chrome, also wiring, electrical wiring for this device. Then this is the device. Then you have need to remove the photoresist. Then you have gold deposited at the side of this. Okay, you have chrome gold deposited. Then for the actuator also need to deposit gold at the side as well. Then we can have this. This is might be considered batch processing because this is one batch of process. You can have this more than, this more a lot than this, but in this figure you can see some six actuator before we cut into single actuator like this. So this is 5 in a strip. Then you can later on dice cut into a single actuator at this side. So this is one single actuator PZT. Then we try to place in between of this stage. Okay, and the bonding, the connection is using electroplating, meaning we are using metal, nickel electroplating to bond between this side and this side. And then you see that the bonding of PZT, then this is an example. Can you motion? Yeah, click, yeah. Yeah. You can see that this actuator work. Yeah, see a little movement when apply a current to the system. This is a bonding pad with wired, and this is actuator placed in between the Muni. Then you have the movement. A few micrometer can be made using this device, this actuator system. Okay. Okay, and this is the, I mean, the whole package that this actuator can make about 16 to 70 micron, 16.5 micron at the applied voltage of 60 volt. So that is part of the device that can be made or can be designed, fabricated using MEMS. Then it can be used in many sensors and actuator system for micro positioning, for accelerometer, etc. So I think this is the future outlook of MEMS as shown. And in summary, MEMS are everywhere, basically, in many applications. Thank you. Any question? Yeah, yeah, thank you. Yes, alignment is very critical, as I keep mentioning. So we must have a kind of marking of alignment. So there is wafer aligner machine. So when we design a pattern on a wafer, we normally will have a alignment marking at two sides. I mean, on the left and right, for example, top or bottom. So then later on, when we try to place another wafer, we get the alignment right, then we can place together. Because when we design, the drawing that we do is aligned because we know the dimension. So, but when we do the process, we are not able to follow the alignment if we don't, by design, we don't have that alignment. So basically, the alignment of the marking is very critical for you to align the bonding and the placing. Mainly by drawing. And we fabricate on the device itself, the alignment. Yeah. Yes. 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 Passive? Passive is just use heat sink without any external force, without any energy required. So it just let it release the heat by itself. So passive. Yeah. Yeah. Thank you. Yeah. Thank you very much.